let Dr. Laterza introduce himself with more details. And thank you very much, Matteo. Please, the floor is yours.
Thank you very much, Adrian. So, well, welcome everyone. A few words first about me. I'm an engineer born and bred. I started in aerospace engineering, both by bachelor and master's, and my PhD. Then, at that point, I definitely turned toward academia for a while. But I can say that my career more or less follows the research and development path, in which I started doing basic research, and then I progress to launch and prepare something for space as part of my postdoctoral work. And after that, I went in the startup, and I'm now thinking about logistics and launch schedules and so on and so forth. Here, it's a small, let's say, snapnet of the technology and research and development course. Of course, this course covers a lot of different topics, and they are dealt with in more or less detail according to what the audience background is. We will try to give a gist in this webinar, and we are hoping to still bring some concept that will wake up your curiosity. The first concept and main focus here is, well, what is technology? Now, my favorite definition of technology is stuff that doesn't really work quite yet. This is because, well, things that don't work at all, that don't exist, well, they're not technology yet. So if we imagine like the warp drive is not a technology, it does not exist. There is some theoretical ideas on how it can be achieved, but not the practical remotely close to working. But then if we think other stuff like, I don't know, planes or phone apps, those are not really technology either. They are a product. They work very well. And if one wants to build a plane, has a lot of specific guidelines and a path to follow on how a plane is built. Then, of course, improvement can be done in something which is already a product, and different products compare each other using specific technology, but the product itself, the main idea, is not a technology anymore. I will use quite liberally a quote from Akin's Laws of Spacecraft Design, because, well, they're funny, but I think they bring in few words concepts that are painfully clear to many people in the field. And the first thing is, you cannot make it better until you make it work. So the idea of improving the product is making it better, but the real, let's say, aim of research and development is making it work in the first place. So bringing it from not being a technology yet to not being a technology anymore. And this is shown by a concept which I'm sure will be familiar to many of you, which is the technology readiness level. So here in this scheme borrowed from ESA, we can see that things in red are not technology yet, while the part in green is not a technology anymore, even if, it's a space rocket. But again, basic expendable launchers are something which now is very much done, while the yellow part is, well, technology, is what research and development is about. And there are many aspects here that bring different challenge, and many anecdotes that could be told, but now for the sake of time, I'll try to restrain myself. We go to the concept of trying to climb the TRL ladder. First is make it work, well, at least a bit, right? We have to bring it to the level of being technology. So it's still a pure research in which we're trying to prove that our concept can work at least in the lab in some way or another. Then parts from 3 to 5, we're trying to make it fit, meaning we have a different set of challenges in which we try to follow what the basic requirement can be. So mass, volume, power, temperature, basic environmental requirement. While in the part from 5 to 7, we are going with a different, again, set of challenges, much more specific requirements for the environment, so launch vibration, temperature in space, radiation, or we start to see logistic thinking such as can it actually be physically transported to the launch site, or can I build it in time? And the part 7 to 9 is again the part in which is not very much a technology anymore, is a product. So, well, can I make it to scale? Can I make it in time? Can I make it at a decent cost? Uh, the first time I gave this course, I actually had a very interesting question, which really represents the core of the problem for the R&D and especially for the development part. And it was, wait, but what if I find out once I actually built my system that it cannot be transported to the launch site? And there are different approaches to try to solve this very real problem. Um, the main and most traditional of which is the V model. So the V model is the quintessential German concept. It's very detailed, precise, and it's a very strict and very schematic. So we start from our requirement, and from the requirement on the function of our system, we can define in general what the form of it will be, setting a sort of specification, and then go down in more and more detail of subdividing the form of our system to subsystem and components, defining those, and define what the testing approach will be to verify these different components, subsystem, system, and ultimately validate the functionality of our system as a whole. And in all this process, as they say, the difference between messing around and doing science is taking notes. So a lot of documents are produced of what the requirements are and what the tests are. This system is quite, well, beautiful, I would say, from an engineering point of view, and in some form of another, more or less faithfully, is adopted in every development effort. The problem with it is that nature can be at times quite a bit messier than this. Uh, the first problem comes with, well, the documents themselves. Documents are written, redacted, approved, and by the time they're actually used, most of the times they're not up to date anymore. Um, what ends up happening is that, well, you tend to just go to the person that actually is dealing with it and you ask him what a number is, what the requirement is. In bigger operations, it can be that every document has an owner which is represented in your Gantt chart and your work breakdown structure, but that simply puts on a formal document who is the guy you end up asking with. To go around this and let's say try to adapt this system for a more fast-paced industry, there is the so-called model-based system engineering, where there is a unique model stored often in the cloud, where all the stakeholders can go and watch their perspective on it and have a updated real-time version of the system, of the requirement, of the test. The problem with this is that it requires a lot of overhead. It needs specific people that maintain this whole system. It needs experience in this, it needs training, and it can be very hard for small entity to approach it. One, well, let's say different and quite scrambly way to solve this problem of figuring out too late that your system doesn't work is rapid prototyping. Rapid prototyping comes from first an opportunity of the modern time and from a problem of technology. The opportunity is simply that now it's easier and easier to actually build prototypes. Once, if you wished a specific, a complicated shape, you needed well, specialized artisan that would hammer your sheet metal until it gets the final shape, and so you can, let's say, well, test with it. Right now, it's easy. You can prototype, you can 3D print, you can buy cost components which are quite cheap, and so prototype your electronics, for instance. And even launching into space is much cheaper than what it used to be. But then we have the problem is that, well, for technologies, so things that don't work quite yet, the numerical models tend also to be very much a technology. So if we take, for instance, the wing of a plane, you have computational fluid dynamics is very good in telling you what the forces will be on that wing. And then the, well, mechanical and structural models are very good in telling you what structure is needed and how much metal and placed where is needed so the wing can actually carry these loads. But if we take, for instance, well, plasma thruster, then we do have numerical model that can predict how the plasma behave inside and what the force will be and what the power and oscillations will be. But trust me, I work on that for quite a few years. I can tell you that model is very much a technology. So often it's best to just test. And often the tests, the early tests, tell you enough that you can iterate in the next model, saving you the cost of bringing this test until the end. So often a lot of the model are tested, but they're not very used. The lesson is brought to the following test. And this can be also be done with whole projects in which the early phases, the early projects, the early products are actually already before being put into use and before being launched, a valuable lesson for the next projects to be developed. To use this approach, however, we have to use, well, we are forced to do simplification, which actually is very useful to do anyways. Now, this is a thing that, for instance, Elon Musk mentions a lot, in which you have to try to remove components and processes, but he didn't not really came out with it. It's something that occurred to many engineers trying to work on this after a lot of failure deriving from high complexity. And yeah, a real design is completed when there is nothing more to add, but there is nothing left to take away. And this can be components, right? There's an old saying, what isn't there won't break, but also processes and simplifying your production chain. But most interestingly, especially for the research and development, is requirement. So often requirements are placed there because, well, that requirement just needs a number, but not much thought is put in there. Or, most importantly, we don't know exactly what the requirement can be, meaning what the resources available are, or what is really possible and not possible because the technology is still under development. So it's always important at every step of the way to be able to reiterate and redefine the requirement to simplify them. a process that helps doing that is the iteration through successful products, not through testing on the same product. So the four
Sorry,
phases of
Matteo.
yes,
We cannot see the screen anymore. Can you please try to?
yes, I can try to exit from the presentation and go back into it. Let me try just a second. Let's close this one. Let's present again. Okay, let's go. Presenter view. Okay, what slide are you seeing right now?
Okay, I can see it now. I'm not sure if the other people can see, but it's the iteration through successful
Yes.
product.
Okay. Okay. Thank you, Chiara. Sorry for an inconvenience. Good. So back where we were. Yes, these four phases, the make it work, make it fit, make it fly, and make it sell, are the same that our original climbing the TRL ladder slide. But truth is that often, especially in with the new ideas and new concepts, we don't really know what the problems are until we encounter them. And an approach that is taken nowadays more and more often, especially again because launches are much cheaper than they used to be, is the one of iterating through products. So you start from a very simple product and you make it more and more complicated once you have experience of where the problems really lie. So you will start with a simple concept and launch it and learn that, for instance, the launch requirement affect your concept. Now your second product, which is more mature and let's say more interesting, will already have those lessons and we will be able to give you much more refined requirements for what are really the volumes and power and materials needed, or well, many things that I cannot imagine right now. It really depends on the product. And so on with the first flight of actually a commercially viable product, you will already have skipped all the hiccups in much cheaper phases of your development. And eventually you have a product that knows very well where the market is places and what the problems are and is ready to deal with these problems. One example about this process is, and the reason actually for its advantages is the Radio Aurora Explorer satellite. And this was a scientific CubeSat that was well measuring the northern lights. The CubeSat was developed, was launched, and once in flight, it found it has some, well, some technical problems, some component failed, and it was still able to perform some science. So the project itself was not a failure, but not only that, it was found out that fixing the problem, building another satellite and launching only increased the total cost of the project by about 10%. Now, if we compare this with the traditional space programs, where the problems encountered during the way can bring the cost of being several times what initially budgeted, and the timelines several years of delay, it's clear that it's an approach that deals with this problem very effectively. And another reason for this approach is very favorable nowadays is the one that we often don't have access to unlimited government funds in modern space. Now that's an interesting comparison between well, industry and academia in the cycle between funds and results. Now, the idea in an industry would be that, well, you start with some seed funds, but you have a product, you have results that you can present to your customer, sell it, and get more funds to do more R&D and to bring more results. While the concept for academia would be that you actually first write what you would want to achieve, what your research want to be, and you get the funds, then you research it, and after the research is finished, you have your result, your publication for which the grant was for. It happens to be in reality that, well, the two things tend to be switched, meaning that you often tend in the industry, especially in fast-paced startups and in other industry that relies on technology, that you sell things that you haven't really built yet. You use this fund to do your research and development really quickly in order to have your results that actually go to the customer. And that's a thing, I say to my boss, you keep making promises that I end up having to keep. Uh, that's a problem, but actually is also a necessity and one of the reasons that startups can actually progress quite quickly. They have this time drive. The interesting thing is for that in academia, actually what happens is that research is done at the beginning with some seed funds scrapped together, and once this research is ready, the results are used to write the grant that is supposed to be for obtaining these results, but then this money are used to actually produce new research. So that's an interesting factor that the expected model actually is reversed with the actually effective model in the two fields. But yeah, the reason it's good that my boss making promises is due to, well, the nature of funding. If there's not a flight program, there's no money, and there is a flight program, there's no time. So in order for funds being there, you actually need to have a program going that then will push on you. But that is necessary because if nothing is happening, your company has no reason to exist. The problem, though, is that well, early startup or early venture of actually any sort, because both academia and startups and traditional companies and also NGO and really any other type of activity requires money, will find out that the problem is not so much finding people offering you money that you would think is the problem, but is what these people want in exchange from you. Now, this part will be actually treated much more in detail in different lecture in the space economy course, which aren't mine. I'm a poor engineer. I don't know much about economics, but I've been in enough board meeting and investor meeting and venture capital meeting to have figure out a few things about the value exchanges. Is that, again, there's no thing as a free lunch, and you have to be very careful what you are giving out in exchange for money. There are things that are very valuable to you as a young company and or really any other activity that depends from technology and ideas. Your ideas, your intellectual property, you don't want to give out. Equity is a thing that you might have to give out, especially at the beginning when you have nothing else. And it can get your investor very much vested in you. So it might be a good idea, but you might lose decision power and you might not be able in the future to express your idea. Another interesting thing is political capital. As we will see in the next slide, well, the funding environment can be much more complicated than initially expected. You have to understand that, well, favors are actually a resource that can be expanded and has to be managed carefully. And latest, Economy 101, products and services. Well, those are the two things you really want to sell, and you're much better off if you can sell services rather than products. But again, people more prepared than you in the final course will deal with it in the more detail. An aspect I want to focus here is how engineering concept can actually be used in the economy part. So this is a very schematic representation, and different institutions actually have been incorporated in one system of the funding ecosystem that at one point of my career I found myself to deal with. And after hearing a lot of acronyms and name throwing around, once I had to sit down my boss and have me explain in detail who's whom and how they're related to each other. And to do that, I used design system metrics, which again is a system engineering tool, but it can be very effective while funding. I wrote down all the different agencies and departments and companies. The one in the dark purple are the one that was actually giving us money directly. The one in green we were cooperating with. And by organizing the design system metrics and putting together ones that have interface with each other, I managed to simplify a bit more the system and try to understand exactly who's whom and how they work with each other. The interesting thing is that the one to focus on are the green scare one, which is, well, the military, surprise, surprise, for space application, which are not the one giving directly funding, but they are the one connective and involved with the one that do give us funding. Other important thing is, well, some unexpected human relations, such as one one entity and the other are not connected in any formal way, but it happens to be that often the officer for one end up working in the other. So eventually, if you have to, let's say, manage your political capital, that's a thing you definitely want to be interested with. Um, Lastly, for engineering and, well, in this case, military concepts that do apply to research and development is the tactics, strategy, and logistics. Uh, it can be very likely, if you're deep in research and development, that your origins are from either science or engineering, and you're very much focused on the technical aspects of problems. How do I optimize an engine? How do I increase efficiency? How do I make this structure lighter? And this is very much the field of tactics. So what actions are put in place to follow the strategy? Then, of course, as a company, you might have in mind what your strategy is and how many years in you want to be before you can make a profit, or let's say, what is the share of the market that you want to take, and so on and so forth. But often, the real problem and the way to be ahead is the logistics, which tends to be the interface between you and the environment. So in system engineering, the interface is the key for everything, and I deal with it much more in detail in the full course. But interesting is how, again, logistics is the interface between you and, well, everything else, including the customers and your competitors, and often how movement, resources, lead times, literal logistic, as in transferring your systems away, or what people can transfer the system, what country can sell to what country, what are the, let's say, security restriction, and, well, many more ideas that won't be clear until you start building something simple and launching it. This tends very often to be the key factor in being successful as an R&D concept. And well, that, I would say, conclude the flash sneak peek in